Welcome to example number 4. This is an example about banked turns. A lot of highways, curved portions of the highways are banked, tilted to prevent the cars from sliding off the highway. When a highway is dry, the frictional force between the tires and the road surface may be enough to prevent sliding. However, when the highway is wet, the frictional force may be negligible and banking is then essential. So what you see here is a banked turn of a car going around this highway. And we're revisiting the same problem before, where the velocity now is 25 meters per second, which we got before. The radius of the turn was 250 meters, and we're looking for what angle must be it banked so that if we don't have to rely on friction, that the car will negotiate the turn. So you can see there's a car here, and we want to draw a free body diagram for it. And we have a force of gravity going down here. And we have now a normal force that is perpendicular to the surface. Remember the last time we were doing that, the previous example, the normal force went straight up. But in this particular case, the normal force is now angled because the ground is now tilted. So we are assuming that the frictional force that is exerted between the road and the tires is zero, and there is some other force that is causing the car to keep in the turn. And if you look closely, you'll see that the normal force is tilted. So there is an inward component of that normal force that is causing it to accelerate towards the center of the circle. Let's go ahead and show the acceleration now. And the acceleration is towards the left here, towards the center of the circle. Now this is often confused. Some people like to think that the acceleration is going down the inclined plane, but no, it's towards the center of the circle. Let me redraw this same picture over here with just a different looking car. And so here once again we have the normal force and then the force of gravity going straight down. Okay, so now we're going to set the axes, in this particular case, going horizontally out and vertically upwards. Now this is a little bit different from what you were doing before with inclined planes where we tilted the axes. But in this particular case we're going to choose that because the acceleration is going to be along this x-axis that we've chosen here. So here, the acceleration is towards the center of the circle, which is over here. That's point C. So that's right here. And you can see the trail of the car is along here in this red dashed line. So it's remaining in the same position vertically on that inclined plane. And so the acceleration is along this horizontal plane that is drawn here. The angle that the turn is banked at with respect to the ground, or not the ground but the horizon, is here given as theta. That also can be shown that this angle here between the vertical y-axis that we've chosen and the normal force is also theta. So now we can proceed by analyzing the forces along the x-axis. So we're going to sum the forces along the x-axis, and we note that there is an inward acceleration, hence a centripetal force, that is caused by something that is causing it to keep going in the turn. And that is the x component of that normal force, or that inward component of that normal force that is causing that centripetal acceleration of ma. So mv squared over r is now equal to Fn sub x, the horizontal component of the normal force. And so over here I've redrawn that normal force and shown the components now, the component that is along the y-axis and the component that is along the x-axis. And it is that inward x component of that normal force that is causing the centripetal acceleration. To get that in terms of the normal force Fn, we're going to use sine theta is opposite, so the x component of that normal force over the resultant Fn. So now we can replace the normal force Fnx with Fn times sine theta equals mv squared over r. So now let's consider the forces along the y-axis. So we'll sum the forces along the y-axis, and in this particular case the acceleration along the y-axis is 0 because the car is remaining stationary. If it is not skidding up the ramp or down the ramp, it is actually along our y-axis remaining in the same vertical position. So the sum of the forces in this case will be 0. So what is balancing out along the y-axis? The common mistake people will make will be say, oh, Fn is just equal to Fg. But no, the normal force is not directly along the y-axis. It is the y component of the normal force minus the force of gravity, which balance out to give you 0. So Fny is equal to Fg. So Fny, if you look over here, is really found by using the cosine, the adjacent Fny over the hypotenuse Fn. So Fny will be Fn times the cosine of the angle theta, which is equal to mg. So now we can rewrite the normal force as mg divided by cosine theta. And we're going to replace this into our expression that we were working with earlier. So Fn is now going to be replaced with mg over cosine theta. So we will get mg over cosine theta times sine theta equals mv squared over r. Now you'll notice now that the masses will cancel out. So once again, it is independent of the mass, so we can design as the engineer banking these turns, and that all cars or all vehicles, trucks and cars, will be able to negotiate it if they were to hit a patch of ice and no friction. So we're looking for theta. You may recall sine over cos is tan. Theta equals v squared over r. And so now what we need to do is solve for theta. So theta will be tan theta will be equal to v squared over r times g. So let's go ahead and plug in. So tan theta equals the velocity we found earlier, which is 25 meters per second squared, divided by the radius, 250 meters, times the acceleration due to gravity, 9.8 meters per second squared. And we're going to get the arctan of that, which will give you an angle of about 14.3 degrees. And that's it for this example.